The eighth recent discovery on the list is that so many highly improbable factors make Earth habitable that it's very unlikely that another truly Earth-like planet exists in our galaxy. The discovery that the Earth is very unusual is no longer controversial. The only question is, how exceptional is it? Is it 1 in a million, or 1 in a billion, or 1 in a trillion, or even more exceptional than that? This slide shows 5 books that I highly recommend on this topic. Also shown is a National Geographic video documentary series called One Strange Rock. An article in National Geographic magazine with the same title also came out in the same year. I think it's important to note that while the authors of The Privileged Planet are advocates of design, the authors of the other books in the National Geographic series are not advocates of design. To start with, I want to highlight for you 2 conflicting concepts that you may have heard about: the Copernican principle and the anthropic coincidences. The Copernican principle is stated by Hawking and Ellis in this way. They write, "However, we are not able to make cosmological models without some admixture of ideology. In the earliest cosmologies, man placed himself in a commanding position at the center of the universe. Since the time of Copernicus, we have been steadily demoted to a medium-sized planet going around a medium-sized star on the outer edge of a fairly average galaxy, which is itself simply one of a local group of galaxies. Indeed, we are now so democratic that we would not claim that our position in space is specially distinguished in any way. We shall, following Bondi, call this assumption the Copernican principle." The anthropic coincidences are aspects of our universe that are finely tuned in ways that allow us to exist and to flourish. With respect to our planet, Ward and Brownlee write, "Most of the universe is too cold, too hot, too dense, too vacuous, too dark, too bright, or not composed of the right elements to support life. Of all the known celestial bodies, Earth is unique in both its physical properties and its proven ability to sustain life. From the biased viewpoint of Earthlings, it does appear that Earth is quite a charmed planet." Ward and Brownlee go on to write, "If some godlike being could be given the opportunity to plan a sequence of events with the express goal of duplicating our Garden of Eden, that power would face a formidable task. With the best intentions, but limited by natural laws and materials, it's unlikely that Earth could ever be truly replicated. Too many processes in its formation involved sheer luck." Along the same lines, David Waltham writes, "The Earth is a precious jewel in space, possessing a rare combination of qualities that happen to make it almost perfect for life. Personally, I no longer have doubts. The evidence points towards the Earth being a very peculiar place, perhaps the only highly habitable planet we will ever find." He goes on to say, "It's almost too good to be true." So this perspective is opposite to that of the Copernican principle. To restate the 2 perspectives, the Copernican principle is that since the Earth is not in the center of the universe, one can conclude that it's an average planet, not special in any sense. On the other hand, the anthropic coincidences indicate that the characteristics of the Earth and its environment are very special in ways that allow life to flourish. This slide lists some of the factors that are required for habitability, such as the type of star, the characteristics of the orbit, the presence of a moon, which is very large and very close, the size of the planet, a magnetic field, and so on. In a moment, I'll cover some of these factors in more detail. But first, I want to introduce a simple framework to estimate how unique our planet is. There are estimated to be a few 100 billion planets in our galaxy. If 6 finely tuned independent factors exist, each with probability of 1 in 100, then we should not expect another Earth-like planet in the entire galaxy. There are estimated to be roughly 10 to the 22nd power planets in the observable universe. And so if 11 such factors exist, then we should not expect another Earth-like planet in the entire universe. To start, an obvious requirement for habitability is that a planet must orbit its star within what is called the circumstellar habitable zone, defined by distances for which water could be present as a liquid on the planet's surface. This criteria also sets a constraint on the ellipticity of the orbit. The size of the planet is also important. In the book Earth by Press and Seaver, the authors say, Earth's size is just about right, not too small that its gravity is too weak to hold the atmosphere, and not so large that its gravity would hold too much atmosphere, including harmful gases. The size of the Earth is also important to enable a sufficiently strong magnetic field and also for plate tectonics. I'll come back to those two topics in a few minutes. In an article in the Proceedings of the National Academy of Sciences in 2013, a paper reported that about 22% of the known planets at that time were Earth-sized and in the habitable zone. I haven't found a more recent value for that, so I'll use that number for our estimate. The next characteristic I'll discuss is the type of star. This is a chart of various types of stars. The y-axis is luminosity or power output, and the x-axis is the surface temperature, which correlates with the size of the star. The range of surface temperature is divided into a series of smaller ranges given by letters. The stars forming a curve in the center of this chart are called main sequence stars. Main sequence stars are fueled by the fusion of hydrogen to helium. Our Sun is a type G main sequence star. Type G stars are a just right size. Stars that are larger are hotter and burn faster and more erratically. Stars that are smaller are cooler, so the habitable zone is closer in, and in that case, its gravity would slow a planet's rotation too much. I'll go over that in more detail in just a minute. 5% of the stars in our galaxy are similar to our Sun. 80% are type M, red dwarf stars, which are highly unlikely to support habitable planets. This slide is a visual comparison of the size of our Sun, along with a type M star, and also with some exoplanets and also Jupiter. One reason that type M stars are unlikely to have habitable planets is a phenomenon called tidal locking. When this occurs, the planet either doesn't rotate or it rotates very slowly as it orbits its star. This is the case with our moon. The moon doesn't rotate as it orbits our planet, so we always see the same face of the moon. If that occurs for a planet in the habitable zone around its star, then the side of the planet facing the star will become excessively hot, and the side of the planet facing away from the star will be excessively cold. This chart shows the habitable zones in blue for our Sun and for a type M star. Also shown is a line in red that demarcates where tidal locking occurs. Tidal locking occurs for planets to the left of the red line. Planets in the habitable zone of type M stars are tidally locked, whereas planets in the habitable zone for our Sun are not tidally locked. Many of the exoplanets discovered recently that are considered to be somewhat Earth-like are shown on this chart. Notice that they orbit type M stars, or else stars that are at the border between type M and type K. Planets orbiting type M stars are unlikely to be habitable for other reasons as well. They're likely to retain high concentrations of the toxic gases carbon monoxide and carbon dioxide that would be detrimental to life. And also dangerous solar flares are more frequent for type M stars. The fraction of stars in our galaxy that are type G is 5%. So that's another value that we'll insert into the calculation. You might wonder why researchers study planets orbiting type M stars, since they're unlikely to be habitable. In an article in the journal Astrobiology, the author Barnes states that researchers study planets orbiting type M stars because there are more of them, and also because it's easier to detect Earth-sized planets orbiting smaller stars. But it's common for news outlets to hype discoveries of planets orbiting type M stars as being Earth-like, despite the well-known fact that the planets would be tidally locked, and the other factors severely limiting habitability mentioned above. For example, this slide shows an article from the Albuquerque Journal in 2015 that reported the discovery of a few planets that are stated to be near twins to the Earth. It states that the planets are Earth-sized and in the habitable zone of their star. But the article makes no mention of the fact that these planets orbit a type M star and are therefore not candidates to be habitable planets. It's common to see reports like this that focus on only a single factor, such as Earth-sized and in the habitable zone, while ignoring all the other factors that are absolutely critical for habitability. There's also a habitable zone for our galaxy. Stars that are too close to the center experience harmful, highly energetic gamma rays, X-rays, cosmic rays, supernovas, and black holes. And the gravity of other stars will perturb the stability of the solar system. On the other hand, stars that are too far from the center lack the elements necessary for life. An article in the journal Icarus in 2001 estimated that 1% of the stars in our galaxy are in the galactic habitable zone. The next critical factor for habitability is the moon. Most people don't realize this, but the moon plays a crucial role in the stability of our climate. This is stated by Jacques Lascar, a French mathematician and an astronomer, who, along with his colleagues, did much of the pioneering analysis on this topic. The moon stabilizes the axis of tilt of our planet with respect to the plane of its orbit around the sun. The current axial tilt is 23.4 degrees plus or minus 1.3 degrees. Without the moon, it's estimated that the variation of the tilt angle would be from 0 degrees to 85 degrees. The other terrestrial inner planets experience large-scale chaotic behavior of their tilt axes. The moon is effective at stabilizing the tilt axis of our planet because it's very large and orbits very close to the Earth. The most widely held hypothesis for the origin of the moon is that a Mars-sized body collided into the Earth in the past, and the cores combined, but the mantle rocks were ejected and eventually coalesced to become the moon. Some of the key evidence supporting this theory is shown on this slide. For example, there's little water on the moon. trace elements and isotopic composition of certain elements are very similar to those on the Earth. There's a deficiency of volatile elements on the Moon, and there's a deficiency in siderophiles like platinum and gold. But for such a collision to have resulted in the Moon, it would have been an extremely low probability event. Ward and Brownlee write, to produce such a massive moon, the impacting body had to be the right size. It had to impact the right point on the Earth, and the impact had to have occurred at just the right time in the Earth's growth process. In a recent survey of debris disks near newly forming stars, 1 star in 500 showed a hot, dense debris disk consistent with a large collision. But that factor must be multiplied by the fraction of collisions that would form a moon with the right properties. Based on a recent article in Nature Communications, I estimate that to be about 1 in 100. The next requirement for habitability is the Earth's magnetic field. The Earth has a strong magnetic field that protects us from harmful radiation from the sun, as depicted in this slide. The magnetic field is generated by a dynamo effect, which occurs due to the motion of electrically conducting fluid material, liquid iron, in the Earth's outer core. The internal heat that generates the molten core is believed to come from accretion energy in the formation of the planet and also from the decay of radioactive elements. Over the long term, the decay of long-lived radioactive elements becomes the dominant heat source. Isotopes of uranium and thorium are the major radioactive elements contributing to this long-lived heating. Those isotopes are present in very low amounts, as shown on this slide. Other consequences of the energy generated by these radioactive elements are plate tectonics and volcanism. Plate tectonics is believed to be another critical factor for long-term habitability of a planet. A recent analysis has concluded that the amounts of these very low abundance radioactive elements must be finely tuned to produce a sufficiently strong magnetic field to provide the protection we need from the sun's harmful radiation, and also to support plate tectonics, but without excessive volcanism. If the amounts of those elements are too low, the result would be no dynamo and no magnetic field. With those elements present but at lower levels than occur in the Earth, a magnetic field would be present but plate tectonics wouldn't occur. On the other hand, if the amounts of those elements are too high, the result will be extreme volcanism, and also that the dynamo gets shut off and no magnetic field will be present. Earth has just the right amount of these elements to have both a sufficient magnetic field and also plate tectonics while avoiding extreme volcanism. The article closes with this statement. It is tempting to speculate that the Earth is habitable in part because it possesses a Goldilocks concentration of radiogenic elements, high enough to permit long-lived dynamo activity and plate tectonics, but not so much that extreme volcanism and dynamo shutoff occur. The radioactive elements thorium and uranium are believed to be synthesized by very rare events such as the fusion of neutron stars. It follows then that the concentrations of these elements will vary within any galaxy. The authors estimate that the concentrations of these elements should vary between 30% and 300% of Earth's values. Their calculations suggest that a large portion of this predicted range in the concentrations of these radioactive elements is not suitable for having both a long-lived, sufficiently strong magnetic field and plate tectonics. From the chart in figure 2 of their paper, I estimate 20% as a conservative value for this factor. And remember, this is only considering the probability to have the Goldilocks amount of these elements. There are many other factors required for a planet to have plate tectonics. Venus, which is nearly the same size as Earth, does not have plate tectonics. A science fiction disaster film was made in 2009 that was based on the idea that the delicately balanced heat engine in the core of the Earth was disrupted. Watching this film may help you appreciate how fortunate we are that our system is so delicately balanced and stable. The just right amount of uranium and thorium is a necessary condition for both plate tectonics and for a magnetic field, but itself is not sufficient. Many other conditions are also necessary for both of these phenomena to occur. For example, the magnetic field requires the right amount of iron. Also, the conditions had to be such that the iron melted and formed droplets that sunk to the core of the Earth. Further, many conditions were required to produce core, mantle, and crust of the right compositions, densities, and viscosities necessary for plate tectonics to occur. This is demonstrated by the fact that Venus, our close neighbor, which is nearly the same size as the Earth and should have the same amounts of uranium and thorium, does not have plate tectonics. Indeed, Earth is the only planet in our solar system known to have plate tectonics. Some other necessary conditions for a magnetic field and for plate tectonics are discussed in the books mentioned earlier. Another factor that's critical for habitability is to have the right amount of water. Our planet has about 0.07% by weight water. According to Ward and Brownlee, if we had even twice as much water, the land would be entirely covered. On the other hand, if the amount of water on Earth was much less, global temperatures would fluctuate too much. They state, thus the planet's remarkable mixture of land and oceans is a balancing act. This fortuitous combination may be the most important factor that ultimately made life possible. Earlier in their book, they wrote, an enigma of Earth's formation is its composition and particular location in the solar system. A grand paradox of terrestrial planets is that if they form close enough to the star to be in its habitable zone, they typically end up with very little water and a dearth of primary life-forming elements, such as nitrogen and oxygen, compared with bodies that form in the outer solar system. In other words, the planets that are in the right place and thus have warm surfaces contain only minor amounts of the ingredients necessary for life. They go on to say that the origin of biogenic elements is a subject of considerable speculation, and that one idea is that those critical ingredients came from asteroidal and cometary debris. They go on to write, discovering how Earth acquired its supply of water is one of the most critical concerns of the new field of astrobiology. As we pointed out in an earlier chapter, water was not abundant in the inner regions of the solar system when planets formed. There was far more water in the outer regions of the solar system than among the inner planets. Where did our water come from? They state that this is still a subject of debate, and that one of the most common hypotheses is that our just right amount of water came from a heavy bombardment of comets. The right amount of water is a critical factor for habitability. but I'm not aware of a way to estimate the probability for that factor at the present time. This is a calculation using values taken from scientific publications for many of the habitability factors. Many other factors are known to be critical, but their probabilities can't yet be estimated. But the values that are available are sufficient to demonstrate the conclusion that the Earth is very rare in our galaxy. Even excluding estimates for having the right amount of water or the right atmosphere, etc., it's clear that there's unlikely to be another truly Earth-like planet in our galaxy. These are conceptual plots to illustrate a key question. How much of an outlier is the Earth? What does the distribution look like? The plot on the left or the plot on the right? As we gather more data on exoplanets, the actual distribution will become clearer. To date, in my mind, the evidence more strongly supports the picture on the left, that the Earth is far, far different from any planet that we have detected so far. This is why the French astrophysicist titled his recent book, Alone in the Universe. Next, I'll briefly recount the story of Guillermo Gonzalez, as it provides insight into the strong opposition of some within the academic community to the notion of design. Guillermo Gonzalez is an astronomer and one of the authors of the book Privileged Planet. In the early 2000s, he was an assistant professor in astronomy at Iowa State University with a very strong record of accomplishment. He had published a large number of scientific papers, and his work had been highlighted in the journals Nature, Science, and Scientific American. In 2004, he published the book Privileged Planet, along with co-author Jay Richards. The book was published just prior to his consideration for tenure. A few assistant professors reacted strongly to the book and collected signatures of faculty supporting a statement against him. They charged that he was supporting intelligent design as a scientific endeavor. The result was that he was denied tenure. As the years passed and data supporting the unique characteristics of the Earth mounted, he was eventually vindicated by the scientific community. One example is the publication of an article and video series by National Geographic called One Strange Rock. The book by David Waltham titled Lucky Planet, and the book by French astrophysicist Jean-Pierre Bibring titled Alone in the Universe are other examples. The article One Strange Rock describes 13 characteristics of the Earth that make life possible. These had been highlighted in The Privileged Planet and in the book Rare Earth by Ward and Brownlee. Next, I'll illustrate for you how the term Earth-like is manipulated by some in the scientific community to achieve a desired public relations goal. This article in the journal Nature was published at the time of NASA's Kepler mission to detect planets outside our solar system. These paragraphs from the article point out that most Earth-sized planets will be around red dwarf stars, and the question is posed whether they should be called Earth-like. The authors point out that such planets will not rotate, so the term Earth-like really isn't appropriate. This paragraph gets to the heart of the issue. It says, the answers to these questions are important because the public relations rewards of planet hunting and planet finding are great. The temptation to hype each discovery is equally large, but so is the scope for confusion and public scorn, especially given the rabid response on some blogs to NASA announcements. Set the bar for Earth-like planets too low, and a string of repeated discoveries could be overwhelming. Set the bar too high, and a planet that meets the strict criteria may not emerge at all. If that were to happen, the Kepler mission would risk being viewed as a failure, which it most certainly is not. So you see, the authors are debating how many factors are needed to merit the term Earth-like. They state that if the bar is set too high, meaning if a planet should have many of the characteristics of the Earth, then no such planet is likely to be found, and people will think that the Kepler mission is a failure. So the authors are arguing that only a few factors should be required, so that it can be claimed that Earth-like planets have been found by the Kepler mission. This slide shows some misleading statements from public media sources on this topic. These misleading statements stem from the fact that they consider only one factor for habitability. Finally, I want to point out the remarkable fact that our planet's characteristics allow us to thrive and flourish, not just survive. From a purely statistical perspective, it's much more likely that we would find ourselves on a planet with just enough factors that we could barely survive. But that's not the case. Our planet provides an environment such that life can thrive. We enjoy mild temperatures, calm weather, abundant resources, and, as highlighted by Gonzalez and Richards in The Privileged Planet, several improbable factors allow us to make scientific observations and discoveries about the universe. The surprising fact that we can thrive, not just survive, is why author David Waltham, the author of the book Lucky Planet, uses the terms precious jewel and almost perfect for life. I'll mention 3 examples. First, while in the calculation above I included as a habitability factor that stars should be of type G, our sun is currently much more stable or less active than other stars within type G that have nearly the same characteristics, such as temperature, rotation period, and metallicity. A recent article reported that the variability in the light curve of our sun is about 1/5 of the average variability of solar-like stars. Solar variability has the potential to affect Earth's climate and atmospheric chemistry. However, since the variability of our sun is so low, it's estimated to have a very small effect, less than 0.2 degrees Celsius. A second example is shown in this slide. This is a graph of data from ice cores from Greenland. The y-axis is the difference of the oxygen 18 value from a standard mean value for ocean water. Lower oxygen 18 values in the ice of a glacier indicates a lower temperature of the ocean at the time the water evaporated. These results, and others extending further back in time, show that for much of the history of our planet, rapid climate fluctuations involving periods of glaciation followed by interglacial periods occurred. However, for the past 12,000 years, Earth's climate has been remarkably stable. This is believed to be due to a combination of many factors, the most important of which seem to be Earth's orbital parameters. Remember, as just mentioned, the sun itself is highly stable. This exceptional climate stability during the last 12,000 years has allowed human society to flourish. It's far better than needed for mere survival. In light of the history of large fluctuations and all the factors that impact our climate, this degree of climate stability in our recent history, to me, is astonishing. Third, while earlier I discussed that our moon is critical for habitability because it stabilizes the tilt axis of our planet, there's another remarkable characteristic of our moon. The moon happens to be 400 times smaller than the sun, but the sun happens to be 400 times further away than the moon. This surprising coincidence produces perfect solar eclipses as viewed from the Earth. Perfect solar eclipses have nothing to do with habitability, but as highlighted by Gonzalez and Richards in The Privileged Planet, they've led to some important scientific discoveries. These include determining the composition of the sun, which led to the study of other stars, testing Einstein's theory of relativity, and discovering that the rate of Earth's rotation has changed over time. There are 65 major moons in our solar system, but the Sun-Moon-Earth system is the only one that has a perfect solar eclipse. Gonzalez and Richards also point out that our location in the galaxy, in addition to being in the habitable zone, is especially suited to allow us to observe the universe. These are just some of the examples of characteristics of our planet that allow us to flourish in various ways, rather than just merely survive. To summarize, this discovery is that so many highly improbable factors make Earth habitable that it's very unlikely that a truly Earth-like planet exists in our galaxy. Further, a very surprising fact is that conditions on Earth are such that we can thrive, not just survive. The exceptional habitability of the Earth seems to be another informational discontinuity.